Testing. Okay, so today I'm going to talk a little bit about the basics of word segmentation and morphological analysis for Japanese NLP. In this case, the book tells us a little bit about tokenization, what type of tokenizers they exist, and what tokenizers are we using on NLP, on text analysis for Japanese. And I'm going to add some examples to that information that we got from the book. First, just some basics. Why tokenization? Okay. Why tokenization is necessary? I mean, we all know that even though we understand text, the computer technically doesn't understand text. We need to give it enough information for it to understand it correctly. And so for that, we need to convert the text to meaningful units so the computer can understand it, they can process it and analyze it. For tokenization, we got two approaches. We got the dictionary-based tokenization, which can be longest match or minimal cost, which is lattice. And we got also the machine learning-based, which is point-based or subword, or as it's known in the Python library, sentence piece, right? We're going to talk a little bit about each one from now on. Okay, so first, longest match method. Longest match method is one of the simplest and one of the oldest methods that we use for tokenization. It scans the whole text, the whole text that we give it to it, and it matches the word with the longest word available in a dictionary. The problem with this is that it ignores completely grammar. So for a lot of languages, like Japanese, is not used because of this, because it is ignoring the grammar. It's only taking the text as what it is, only text, which can hide a lot of the hints that grammar can give us in the context. For dictionary-based, we got the one that is being used right now for Japanese, which is minimal cost or lattice. It is the most used right now for Japanese. We are also using for some other tokenizer for ML, but this one is the most used, which is the ones it's being implemented in Sudachi and Mecap. And what it does is that it creates a network of all possible patterns of a text. I'm going to show an example to show exactly how it works, but right now just bear with the explication. Creates a network of all the patterns possible for a text, and then they uses an algorithm, which is Viverti, to find the path that minimizes the total cost of the base based on the word frequency. With that, it can know when to separate the words. For example, one of the problems with Japanese is this tongue twister that I have right here. Sumomo mo, momo mo, momo no ushi. There's a lot of mo right there, right? So how the computer can know exactly which word is it if we don't have kanjis? In this case, I'm going to use a self-made dictionary, but normally we use a library from Python. I'm going to show that later, but just to have an example of how lattice works. We have a dictionary here. For people that don't know Japanese, so momo, it's Japanese plum. Momo, it's peach. Uchi is inside something or family. It depends on the context. And then we have some particles, some connectors that are mo and no. So having this dictionary and having this sentence, which is sumomo mo, momo mo, momo no uchi, we can know how lattice is making the whole network of words. For example, here we can see that the first su, after checking the dictionary that we have, it's going to be matched. It's going to be matched with sumomo because it's the only word that has the su inside the word, which has a cost that I just added for explanation purposes, right? And then we're going with the most interesting part and why lattice is so good at using creating tokenization. We got mo. As you remember, mo has a lot of iterations in this sentence. So what what Lattice does is that it gives you every single option of where mo is in a word. For example, in this case, we have momo and we have mo. So after getting this information, after getting all of the instances, all of the patterns that a word can have inside a text, Viverti, another algorithm, comes and just starts checking. Okay, this first node is going to be only with Sumomo and has this cost. That's nice. In this case, we have the second node that has two different costs. First, we have Mo, which is only a cost of 2,000, and we have Momo, which has a cost of close to 5,000. Because of this, it's going to select the cost of 2,000, because the idea is that it's going to go with the lowest value possible. And after doing that, it's able to transverse into an optimal and lowest cost path for the whole sentence. That's how, basically, in raw words, Lattice works. Okay, so after explaining that, okay, just to finish up with this part, what is important, what we need to remember is that the important part is that we are able to have all the hypotheses on how a word can be combined or how a word can be permuted in a sentence. That's why it is really nice for words for Japanese. Now we're going to talk a little bit about other type of tokenization.
Just one question. So on the Lattice, correct?
Uh-huh.
We should go for minimum or we should go for maximum?
For minimum. Is lowest minimal cost.
So in that case, then we will actually miss out the longest word, right?
Uh-huh.
We're taking only the subwords.
It's going exactly, but it's going to go per permutations. For example, let me show you. Let me see something. Okay, I don't have it here. Okay, so what you mean is, okay, what do you mean exactly with?
Suppose like I'm having just like take my name, it's
Uh-huh.
Okay.
Uh-huh.
So there is actually like word bar.
Exactly.
Then another T.
Exactly.
Actually look for the longest word, the right word.
Uh-huh.
So when I'm going for minimum, then in that case, like that Bharati would be like split into bar and T. But if I go for the maximum only, I will get the Bharati. So should I select with the here Su or Sumo?
Okay, in this case, I mean, I don't understand what you say, and what is important here to. Where is my presentation? Huh? Okay. Oh, here's my controllers. Excuse me. Here, when it comes, what comes helpful is the dictionary, because in this case, I mean, I just added this for this example, right? So it's going to know exactly where are the values depending of the frequency inside the sentence. Depending on the in your case, if you're saying Barati and we have a sentence that is using the word bar for some physics kind of theme or kind of topic, because of the frequency, it's going to know that, okay, for example, when we have bar or we have Barati as a whole sentence, first it's going to go for the lowest value, which is bar. After filling that value, since the frequency is going to be low, it's going to go for the next one, which in this case is going to be Barati. So it's going from the lowest value to the next one to the next one in terms of frequency.
Okay.
Okay. So after that, as we were talking before, we have also the ML based tokenizers. In this case, we have pointwise, which is basically a tokenizer that splits the words, and it doesn't require a dictionary, which is something nice, but the problem is that also can lack a little bit of context because of this. And there are some tokenizers that use this, like Kaitia and Vaporetto. We can see here the same type of sentence that we used in the last example. It's going syllable by syllable, and because we have it's going syllable by syllable, and it's splitting in the right places. Now, in this case, it does it based on the context, but in the other case of the other ML-based tokenization that we have, so words or sentence piece, it does it on the frequency. And here's happens something funny. Since, as we can see, since we don't have a dictionary in this type of MLs, we have sumo mo 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 sumo mo 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 no uchi. We see that first, of course, the most frequent character is going to be mo, and it's going to become middle pair. Mo plus mo, it's going to become momo. And then it's going to separate it. Okay, su, momo, 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 momo no uchi. Which technically is correct, but here comes the problem. Even though the tokenization is good, it's going to help for any type of NLP in Japanese, we have the first token that is going to be only su. Since we don't have the dictionary and we don't have grammatical rules, it's not going to be able to tokenize it correctly sometimes. A lot of the times it does, but it may happen that it doesn't. Okay, so just to have a little bit of a summary of these tokenizers. We have longest match, which is easy, but ignores context. It is really fast. We have minimal cost, lattice, which is the one that it is basically the one that we normally use for Japanese, which is high in accuracy, and it's being used by Makeup and Sudachi, which is what we use normally. And we have also the other two options, which are pointwise and some word or sentence piece, which are built for machine learning tokenization. Okay, now we need to take something in consideration. How do we evaluate accuracy? In Japanese, we need to evaluate accuracy based on the generated token themselves. So in this case, we use the position, which is the correct tokens divided by the total tokens of the output. And the recall is going to be the correct tokens divided by the total true tokens in the output. Just to take into consideration. Okay, so now we're going to talk a little bit about Fugashi. A lot of people know it here. A lot of people have used it. It is a wrapper for the Makeup tokenizer, and it access an API which has all the information for the tokenization itself, and it needs a dictionary. In this case, normally the dictionary we use for Japanese is unidic./slide, and it's really good at extracting the morphological features of a text. For example, here, yeah, I should have been better to have the code, but I'm going to do it this way. Here, from Fugashi, we can extract the tagger just to get to know how does it work. As always, I'm going to use the same sentence just to maintain the same example in the whole presentation. And what we're going to do is use Fugashi just to get to know how the tokenizer is going to divide every single word, and it's going to output it, and then it's going to output that. With that, we got exactly this. First, we can see that it does it in order. sumomo mo, momo mo, momo no uchi. And we can see that it's being every single part of the sentence is going to be well tagged. It's a particle, it's a noun, particle, noun, noun, particle. And also we have some sub-position or sub-tagging system. So it has more context. The common noun is a binding particle, common noun, binding particle, binding particle. With all this information, we have the whole context of the word. And also we have the meaning of the kanjis. And that's how basically tokenization works in Japanese. Thank you for your attention.
So this Fugashi supports which are the dialects?
Inga-san. Dialects? Fugashi supports with other dialects.
More.
The Fugashi library is like which are the dialects it supports?
I mean, it's on the context.
Yeah.
I think all of them are basically based on standard Japanese. Knowing the attitude towards dialects, I think all of them probably were created on the basis of standard.
Okay. And like the lattice that you actually like shown, how different it is from the typical Markov chain models? Means, did you hear about Kennesaw language model, Kennelock?
Kennelock? No, I haven't heard about it.
Okay, maybe like when we do the Google
Uh-huh.
type ahead.
Hmm.
So in the type ahead, we actually like as we type, whatever the next code is actually like maximum given, that
Uh-huh.
frequency would be taken.
Uh-huh.
Fundamental, that is Markov chain model. So when we actually like try to type each word, the maximum frequency is taken to have the maximum likelihood.
Mm-hmm.
But in lattice, it is just reverse. We are trying to take the minimal cost. So, like, why we should go for Japanese? We should go for a minimal. Do you have an idea?
I don't have any idea per se, but just thinking about it. I mean, I know that, for example, for character-based implementations like IME, which is the implementation that we have for Japanese in computers in general, it goes for the maximum frequency. But
Yes.
in this case, it goes for the minimum frequency because IME, what it does is look for from hiragana to kanjis, right? So it goes for the maximum frequency, which is the most used kanjis, the most used symbols in Japanese. But in this case, since it's going from hiragana to just understanding what it is, it's going to go with the minimal cost because it's going to try to divide and make sense of every single symbol that we have. In this case, mo, so it has sense in the sentence. That's why it needs the that's why it needs a dictionary. But what I'm thinking right now, lattice diagram. Yeah, when Vivarti comes and just takes the information from lattice and gets the lowest value of the pattern for the sentence. How to explain this? Okay, let me. Okay, here is Okay, it's going to go character by character, right? So in this case, we can say it like this. Since we have a dictionary that says that sumomo is going to be with this value, after it being selected from the Vivaldi logarithm, it's going to be basically not an available option for the next character. So the next character is going to have mo. In the case that, for example, we have mo, which has two options, right? First, it's going to go with mo, because most likely when a character is alone in Japanese, it can be a connector. Mo, ga, the other connectors that we have, no. Yeah, ni. Yeah, I'm trying to remember my connectors. So first, it's going to go by the connectors, and then it's going to try to see if there's a word that it can use mo at the beginning. So that's why I think it's going to go by the lowest frequency first, by the lowest value first, because it's going to be the most likely to be a connector. It marks down the connectors. It thinks that it marks down the connectors, and then the only things that are going to be left are going to be the words in Japanese.
Okay. Try to understand. The list not clear, but I will try to understand.
Okay.
Like, but the cost is not the frequency. It is actually like some computed in a predefined way.
Exactly. I mean, I used this cost just to have an example, because we cannot access the cost in the Unidic /slide.
And just coming to the byte encoding, in that when we actually like calculating the subwords, right? That subwords is actually designed based on the metabolum.
So if I remember correctly, from my own NLP classes, the cost usually is for this, like typically for Japanese speech taggers or like the word splitters, it's calculated by first getting the frequency of a word, and then getting the cost of this is the cost of so you have weight of each word, and also the cost of how close or how much is it possible that two words can occur together. So that's why you have so let's say you have sumomo. So the algorithm first checks if there is a word su in the dictionary in the momo, right? So it can actually find su and momo, but these are two perfectly viable words in Japanese, and it calculates. Okay, so is it better to have what will be the cost, the overall cost? The cost has to be the smallest, right? Right. So is it better to have separate su and momo, which will add the frequency of both words and the cost of connecting them, versus having just one word sumomo? And well, apparently the cost here, the lowest cost will be just to have the word sumomo, right? And it goes like for all of the words like and both the frequencies and costs, or like the collocation cost, right, are just calculated from corpus.
So it's a kind of inverse relation.
Inverse.
It's like a pyramidal.
What do you mean by inverse?
Which means like the rare words will get the highest weight, highest cost.
The cost, so the cost has to be the smallest, right? So the smallest the cost, the more like the highest probability of this is to become like a one string.
Oh.
Okay. Any other questions? Okay, I think it's good. It's good.